Okay, so today's topic is kind of the last one in a group of topics that really all kind of go together. The first 5 really are one big group. The next topic we're going to do after this is on stoichiometry. And I mentioned it yesterday during our lab. I'm just going to make a YouTube video on stoic because stoic is one of those kind of skills that either you kind of remember how to do a stoic sort of thing. Well, like you guys are looking in the back room, my grade 11 class last year, we've just recently done stoic. Right? It usually is a liters times by a moles per liter times by a ratio, and then something goes on the end. I don't know what goes on the end. It's usually like 1 over liters. It could be grams per mole, but that's how stoic works. Okay. So on Friday, on Flex Friday, at some point, watch my YouTube video. But it's kind of just a rehash of something that you probably already know. If you guys in grade 12, if it's been a long time and you kind of are needing a refresher, make sure you watch that video at least once, okay? So after this lesson, though, the course takes a decidedly a big change. We then focus on a very technological aspect of electrochemistry. We're going to talk about batteries. Okay? Because that's really the next section is once scientists manage to figure out all of the inner workings happening with electron movements, then the question is, well, what can we do with it? And the technical term for a battery is called a cell. So we're going to talk about cells and one more number. On this chart thing that I've had you guys work with, there's a whole bunch of numbers off to the side. We're going to talk about that. If you know anything about batteries, you can see the units there are in capital V's. V stands for voltage. So we're going to talk about how batteries have a certain amount of voltage. Does that make sense? So this lesson here, though, kind of rounds off the first half, which is more of like the theory side of electrochem. And then we're going to move into the application side of it next. Does that work? So today's topic, then, is actually one that maybe on the surface seems a little insulting. I'm going to teach you how to balance reactions. And you might think, hang on, I've been through grade 10 and grade 11. I know how to balance equations. And not that I want to disrespect your abilities to, but sometimes balancing redox equations is actually very challenging. So what I want to do is I want to add to the methods you already have. Okay. So far in terms of balancing, I've actually only really taught you one method probably, which is look at the equation and just kind of put some numbers there just by like your brain. If that makes sense. Like I actually find it very tough to teach balancing because I'll kind of say, hey, look, shouldn't you put this here? And I'll be like, isn't it obvious? And hopefully you'll nod and go, yeah, it's obvious. You should put it 2 there, right? But some kids, like, they don't pick up on it, right? But that's really the only method of balancing I've ever shown you, which is just, I don't know, just do it. So sometimes you'll actually see that referred to as balancing by inspection is the phrasing you'll see in a textbook or in a curriculum. So what I want to do is I want to add to your balancing abilities. I want to show you some other techniques that you can use because you're going to get asked on the diploma a question about balancing. There's a good shot it's going to be numeric response where they're going to give you an equation. They're going to leave you like the blanks in front of the different numbers open, and you have to figure out what those numbers are. And sometimes you can just look at it and go, put a 2 there, put a 3 there, put a 6 there, we're good to go. And sometimes it sucks and you're stuck in this never-ending loop. Anybody ever been in a loop where you're like, put a 2 here, put a 3 there, put a 6 there. Oh, shoot, can you make that a 4? And it never works. Okay, so that's today. I'm going to show you some methods to help you with balancing.
Mr. Forster, okay. You have a call on line 1. Mr. Forster, call on line 1.
Okay, distractions galore today. So basically my notes look like this. Big slide with some steps on them, which I'm going to skip because you guys can read them. And I'm going to show you 4 different methods. Okay. So the first method would be try to balance an equation by looking at the data table, like the transparency sheet that you have in front of you. So let's try an example here. What was that? I am recording this, yeah. So I'm just going to hop right to the example, and then we can just look over the steps as we do it. So you've got a dichromate ion. It says it's a good oxidizing agent, and it's going to react with tin in an acidic solution. Let's try to write a balanced equation. So the first thing you may want to do then is something similar to before I kind of was gone for that week. Find stuff on your data table. So you need to find where the dichromate is. Again, hopefully the more practice you have, the better you are at just kind of instinctively finding where things are on the table. Dichromate is right here, Cr2O7. It also says that it reacts with the tin 2 ion. So then we got to find the tin 2 ion. And it's actually located right here, which is not useful because both of those are oxidizing agents, and we need one to be a reducing agent. But then the tin 2 ion is over here as well. Technically, we could probably circle a few other things. Like, I like to suggest you should always consider water. Because if anything is an aqueous solution, it is possible that water is part of the reaction. And one more thing, it said it was an acidified solution. What does an acidified solution mean? We have H+. Okay, H+ is on this thing like 7 times. More than 7 times, about 15 times. But I think really what's important here is it means that we have the H+ needed to go with the dichromate. So hopefully you can kind of see then that we have a spontaneous reaction there. Does that make sense? Technically, the dichromate could actually react with water. However, because there's tin present, the dichromate will actually react with the tin first. Does that make sense? This is actually a consideration. It's actually one of your post-lab questions. Water, certain things, water cannot be the container that you put it in. I didn't phrase that very well. Yesterday, we talked about sodium. Remember how I had that jar of sodium? The sodium wasn't stored in water. The reason why is that sodium reacts with water. Does that make sense? You could not put a dichromate solution inside water because the dichromate would actually react with water. Does that make sense? Technically, actually, dichromate on its own is fine with water, but as soon as you add some sort of acid, then it actually becomes a problem. So, anyways, I'm getting away from myself. Here's what I can do then. I now have 2 different half reactions. Let's try to fit them together. Now, the most important mistake that I want you to avoid is you have to flip one of the reactions. So if you're looking up for things in your data book, make sure you flip the correct equation. So I'm going to write the Cr2O7, 2 negative, aqueous. Then it was, what, 14 hydrogens? Where is it? 14 hydrogens. 6 electrons. And it makes 2 chromium 3+ ions. I should have saved more space. There. And what did it say? 7 waters? 7 waters. Does that work so far? Okay, and then, like I said, we've already kind of done this method here. Then find the other reaction. But make sure you flip it the other way, because these are all written as reduction. We need one to be reduction and one to be oxidation. So find that tin equation, and start with this tin and go backwards to the tin 4+. Maybe I haven't talked about this, but do you guys see the sign between here? This arrow right here? It's a double-sided arrow. If I haven't pointed that out already, basically the concept is that you can use the reaction going forward or backwards depending on how you need to. So that's the symbol for like a 2-way arrow. So have your tin 2+, go backwards into your tin 4+, and 2 electrons. So far, so good? Quick reminder, I've been doing this with you guys hopefully for a couple of, maybe even as much as a year and a half now. States of matter really matter. Don't be sloppy, because there's a difference between a 2+ and a 4+, and there's a difference between a solid and an aqueous. Does that make sense? So write down those little states of matter. Try not to be lazy. Any guesses as to what our next step is? Good, yeah. Basically, you got to find a way to make sure your electrons cancel. So if you triple this, and make that a 6, now your electrons are balanced. Does that make sense? So, if done correctly, this should now yield a balanced chemical equation for you. So it should look something like this. 1 Cr2O7 And just a talking point here, you don't have to write the 1 there, but just make sure you're aware that it's a 1, not a 0. Big difference there. 14 H pluses and 3 SN2 pluses need to turn into 2 CR3 pluses, 7 waters, and 3 tin 4 pluses. That should now yield a balanced chemical equation for us. And I could totally see a diploma question where they give you the equation here, and they just leave out the coefficients in front, and you've got to figure out that it's a 1, a 14, a 3, a 2, a 7, a 3. It is possible, in theory, for you just to look at the equation and just kind of go, yeah, put a 2 there, put a 5 there, put a 7 there. Like, you can try it that way. But sometimes I need to show you just some other methods to help you out in case you get stuck. Okay, one last thing. It sure looks like all of the elements are all balanced. Like there's 2 chromiums to 2 chromiums and 14 hydrogens to 14 hydrogens. But this is more of a physics topic, but there is a law of conservation of charge. So whatever charge you have before on the reactant side better be the same as the charge on the product side. So you should always double check to make sure that your charge adds up. So for example, there's 2 negative right here. Then there's 14 positive, so that makes 12 positive because the 2 negative cancels. And then there's 3 times 2 positive more. So what does that make it? 18 positive on this side over here. And then if I check this side, you've got 2 times 3 is 6, and 4 times 3 is 12, and 6 and 12 is also 18 positive. So charge is balanced. So make sure the charge is balanced as well, because if they don't balance, then it's not correct. So far, so good? Okay, so that's one method. You can use the equations in your data booklet. Here's the reason why I feel like I have to have this lesson, though. You might be saying, okay, Chris, that's great, but I mean, we already learned this. They're probably going to try to throw you a curveball and make you try to solve something that's not on this sheet. Does that make sense? Because it's too easy, right? I mean, if everything's on this sheet here, does that make sense? So that's why I need to show you some other methods. So B, let me do an example where you're going to have to balance a redox equation under acidic conditions, but the other little, I didn't have enough room because there's already 7 words on there. But like the other little thing you could add to that is, and these aren't going to be in your data booklet. So that takes away that crutch of being able to look on that one sheet there and just fit them together like that. So let me show you another method. Sorry, I'm just going to check and see if that's my wife. Maybe so. Very good. Okay. So first step basically here is that we need to start writing out a skeleton sort of equation of what's occurring here. It says that aqueous dichromate ions react. So I'm going to start by writing out what a dichromate is. Do you remember what dichromate was? Yeah, so start with a Cr2O7. And I'm going to kind of gloss over some of the other things that are occurring here. And I'm just going to look for what logically could the dichromate ion turn into. Could the dichromate ion turn into the nitrate ion? That doesn't really make sense, does it? Because nitrate involves nitrogen. But wouldn't it make sense that the dichromate could turn into the chromium ion? So I'm kind of just going to start by making like a base equation to begin with. But then I have to do it twice, because there's going to be 2 half reactions that go together. So it also says that we have nitrous acid. What's nitrous acid? Good job. Yeah, HNO2. In case you've forgotten the rules about acid names, nitric IC is anything that ends in an 8. I ate something icky. And nitrous, when you get into a fight and you get punched, you say us. And so it's an ite. So you need nitrite, which is NO2. It's silly, but it works. I think it works. Hopefully logic would dictate then the nitrous is probably going to be the thing that makes the nitrate ion. So I've started out here by kind of just making kind of a base skeleton kind of equation. but I've done it twice. One of these is going to oxidize and one's going to reduce. I don't know which one is which yet, but I will hopefully get to that point. So, is everybody okay with that first starting bit? Okay. Now, if you try to look for these in the data booklet, by the way, you'll discover that HNO2, I don't believe, is listed in there anywhere. So that's what makes this a challenge, is you can't just find this equation somewhere. I don't think HNO2 is sitting in there. So I'm just going to actually show you the steps here. First, write out the skeleton equations. Step 2, then, balance all of the elements other than hydrogen and oxygen. We're going to leave those ones for last. So, for example, right here we have 2 chromiums. Here we have 1 chromium. So put a 2 there. I balanced the chromium. And on the bottom equation here, here's 1 nitrogen. Here's also 1 nitrogen. So I'm good with that step. Still good? Okay, next step. Balance the oxygen atoms by adding water molecules. Okay, so if you can take a look at this equation right here, our chromiums are balanced, but here there's an oxygen, and there's no oxygen on this side over here. Well, a common source of oxygen, because we're using aqueous solutions, is water. Water is plentiful. So I'm going to throw water on this side over here. And the water is what's going to help keep the oxygens that are over here balanced. But there's 7 oxygens over here, right? So I need 7 waters over here. Does that make sense? And let's do on the same reaction on the bottom here as well. Here there's 3 oxygens to 2 oxygens. Now a common thought you might have, don't write this, would be 3 to 2. Okay, put a 2 here, put a 3 here. That's not going to work. Because now you've goofed up your nitrogens. Because now you have 3 nitrogens to 2 nitrogens. Does that make sense? And this is where you might get stuck in that loop. You know what I'm talking about there? Hence the whole reason for showing you this. So the other way of fixing this is, rather than trying to add and fix the nitrogen-oxygen problem that way, add a water to this side right here. Because if I had 1 water over on the reactant side, again, keep in mind, water is plenty. These are aqueous solutions we're likely working with, so water is available. Now I have 1 oxygen plus 2 more over here, makes the 3 over here. Does that make sense? All right, next step. Balance the hydrogen atoms by adding H plus when needed. Okay. When you're balancing an equation, you basically have 3 options. It's either a neutral solution, which means that there's no hydrogens or hydroxides needed, or it's an acidic solution, or it's a basic solution, right? I mean, either the pH is above 7 or it's below 7. It's got to be one of the 2. And if you remember from grade 11, even neutral water technically can break up into hydronium and hydroxide 2 times out of a billion. You guys remember talking about that at all? So really, if we need to, we can add hydrogens to both sides and make it acidic solutions to make the hydrogens balance. Because hopefully you'll see right here, there's a whole bunch of hydrogens right here, and we need to find a way to balance that. So to do that, I'm going to throw 14 hydrogens over here on that side. It's in an acidic condition. It says as much. So to fix these 14 hydrogens right here, put 14 H pluses over here. What should I do in the bottom equation? Similar. How many? Yeah, I agree. Yeah, because you have 1, 2, 3. So you need 3 hydrogens there. In this example here, the acidic condition is required to get the equation going. In this example down here, the acidic conditions are actually produced afterwards. Okay, and then last step, well, not last step, but next step here, we now need to balance the electrons. So this is probably the one that kids find the most challenging. We have to try to figure out where the electrons would need to be to make these equations balance. So stop me if I lose you, okay? Right here, you've got 14 positives and 2 negatives. So this side currently has 12 positive on that side. Does that work?
You guys aren't doing something stinky, are you?
Not today.
Okay.
Do you want us to?
No.
Okay.
No, there's just something stinky in your mind. I was my first.
There's something sticky what?
There's something stinky in I was.
Oh, you're seeking out the smell.
First.
Ouch.
Not you personally.
Not us. Okay, on this side right here, hopefully you'd agree there's 6 positives. Does that make sense? So, hopefully it's visually obvious, hopefully, that our charges don't balance. So we need to put some electrons on one side or the other to make the charges balance. Then we figure out where the charges would need to go, where the electrons would need to go, and how many. 6 on this side. Does that make sense? Because if you were to add 6 electrons right here, that would then drop this guy back down to be a 6 positive. Does that work? Okay, I lied a little bit. This first equation is actually one in your data booklet. So we probably could have cheated and written that one out. But I just wanted to show you the process. But I don't believe this bottom one is in your data booklet. But let's use the same process then. What is the charge on this side over here? Actually nothing. Technically it's neutral. What about on this side right here? Well, no, there's 1 negative right here. And then there's 3 positives over here. So it's actually +2. So how do we turn a 0 into a +2? I add 2 electrons to this side right here, and that should drop the charge back down to neutral. If you do this properly, you better have electrons on opposing sides. Because if you have electrons on the same side, then Hess's law isn't going to work. How am I doing? You guys still able to follow? Okay, so now we're at the stage where we've been at before. You need to start canceling. But we're not there yet, though, because 6 electrons and 2 electrons don't fit. So triple. So triple this guy, triple that guy. We're good. Thanks. Triple this one up to 6, triple that one to 3, and triple this one to 9. Does that work? And then now the electrons should cancel. One more thing. We have to be a little bit more careful though with Hess's law this time, because we've been adding water and high H+ ions, and they actually have the ability to either combine or cancel as well. So now when I want to put this final thing together, yeah, there's 14 hydrogens right there. But see how there's 9 sitting over here? So how many are left? 5 hydrogens. Because the 9 and the 14 will subtract, right? You'll have 1 dichromate ion. Sorry, I'm a little bit lacking in room here. You also are going to need 3 HNO2s. Okay, there's 3 waters sitting right here. But there's actually 7 waters on the product side. So we don't actually need any water on the reactant side. We need to make 4 waters show up on the other side, on the product side. That makes sense? You're also going to need your 2 chromium ions. You're going to need your 3 nitrate ions. And I think this hydrogen right here is already canceled. So I think that's it now. There, we've now written a balanced redox equation. So the coefficients are 5, 1, 3, 4, 2, 3. Something along those lines. Do you guys see why there's kind of a need for a lesson like this? It's probably going to be too challenging to just look at an equation and just by sight, just go put a 3 there, put a 4 there, put a 1 there. Right? Like it's doable, don't get me wrong. But it can be challenging. Partially because when I first started, I wasn't aware that I was going to need 5 hydrogens on this side and 4 waters on that side. Like when I first started, all I had was this guy, this one, and that one. Does that make sense? So I wasn't even fully aware that I needed to have this hydrogen and that water. Does that make sense? Okay, cool. Let's try another one. So this next one here involves similar steps, but I'm showing you this in case it needs to be under basics conditions. So it is possible that you're asked to do something with H+s, but you guys might notice that on that sheet in the data table, a lot of these equations here involve an H plus, involve an H plus, involve an H plus, but there's quite a few that involve OH minus, OH minus, OH minus, OH minus. So it's also possible that you might need to balance something that somehow is under a basic condition. So let's try another example here. Basically start the same way we just did. Let's try to figure out what logically kind of fits together. So it says you've got solid chromium 3 hydroxide. Okay, well, chromium 3 hydroxide will be CrOH3 solid. Right off the bat, I'm fairly familiar with that particular table. I don't believe chromium 3 hydroxide as a solid is on that table. Makes sense? If it was, I would try to use that thing to help, but it's not useful right now. So, what do you think the CrOH3 is going to turn into? Is it going to produce the chloride ions or the chromate ions? Probably chromate, right? So what's chromate? What's chromate? Everybody? Good. It's CrO4. Where did you find it? Yeah, you know in that little blank section in the middle of the periodic table, there's all those polyatomics. Chromate is one of them. CrO4 negative. Is that correct? 2 negative? Okay. Just want to double check on that. And then dichromate is also 2 negative. Okay. For some reason I thought dichromate was 2 negative and chromate was just 1 negative, so sorry, I don't mean to doubt you. Okay, if it's okay, I'd actually like to just start working with this half reaction just on its own right now, doing the exact same steps. So step 1 now was balance the non-hydrogen oxygens. Okay, we're done. Because chromium's 1 and 1, right? Now balance the oxygens. There's 3 oxygens right here and 4 oxygens right here. So how do I solve that problem? Add water, yeah. Okay, I know I'm kind of running out of room here, but let's add a water on this side right here. Now I should have 1, 2, 3, 4 oxygens to 1, 2, 3, 4 oxygens. Okay, well now I have a problem though. I have hydrogens as an issue. There's 1, 2 hydrogens right here and 3 more right there, so I need 5 hydrogens. So I know it says it's under basic conditions, but I'm actually going to keep doing the same step. I'm going to add 5 hydrogens right here. And then the last step, we need some electrons. So hopefully you'll agree this is a neutral compound, neutral compound. Again, states of matter and charges really matter because if you miss the slightest little dictation note on this one, you'll screw up your charges. And if you screw up your charges, the whole thing's shot, right? So this stuff all here is neutral. On this side right here, hopefully you agree there's a +3 net charge. So how do I turn a neutral and a +3 into each other? You're going to want 3 electrons over here. There you go. I've written out my equation. Well, it's actually half an equation. Okay, but here's the issue though. This isn't under basic conditions. This is under an acidic condition. So the last step here is to show you how to solve the conundrum of how to make it no longer acidic. And this is more like you gotta approach this from a math point of view. Okay? In math, you're allowed to divide both sides of an equation by 2. You're allowed to add 7 to both sides of an equation. You know what I mean? Like some of those skills. So maybe just watch what I do here and you'll see why this is going to work in a second here. What I'm going to do is I'm going to add 5 hydroxides to this side. And I'm going to add 5 hydroxides to this side. Mathematically, isn't that valid to add the same thing kind of to both sides? Okay. The reason why this is useful, the reason why I chose 5 hydroxides, what will happen when 5 hydrogens combine with 5 hydroxides? It's going to make 5 waters because it's going to neutralize. So what I can do now is I can kind of cross this stuff out right here and say we now actually have made 5 waters. I'm just going to undo that and show you one more time here. So at this step right here, mathematically, think of it as adding 5 hydroxides to this side. 5 hydroxides to this side will neutralize with your hydrogens and make you 5 waters. But just don't forget to add those 5 hydroxides over on this side then. One more thing. Before I even go any further, I can actually reduce this equation a little bit now. Anybody see the thing I'm referring to, where I can reduce this a little bit?
Cancel the water on both sides.
Good, yeah. There's 1 water that I put over here a long time ago. But now there's 5 waters over here. So I got ahead of myself. You can remove this guy and turn that one into 4 waters. I've now written an equation under basic conditions. I know it's a bit of a mess, but hopefully you guys can follow along. This guy and the hydroxides will turn into this one, waters, and 3 electrons. So here's my first one. So far so good. Okay, let's do the other half equation. If done properly, what should the electrons happen with? I didn't phrase that well. Where should the electrons be? Yeah, on the, what is that, left-hand side? So let's try the next one. It looks like there's some aqueous chlorate ions. Chlorate is ClO3 negative. And it says that chlorate is going to turn into, well, it's not going to turn into the chromate, right? That's not logical. So it's probably going to turn into the chloride ions. So that's kind of the stem that we're going to begin with. Do the exact same process. Okay, so step 1, balance your non-hydrogen oxygens. Done. Chlorines are balanced. Oxygen, there's 3 sitting on the left-hand side, so I'm going to add 3 waters over to this side right here. That'll fix my oxygen conundrum. Now I have a hydrogen issue. Hydrogen, there's 6 hydrogens over here, so I'll just kind of write it over here in the corner. 6 hydrogens up there. And lastly, we need to figure out the electrons. So there are 6 with a negative, so that's like a 5 positive over here, and there's a -1 over here. So hopefully you're already in agreement. We need electrons on this side over here. How many do you need, though? Not 4. You need 6. Because you got to try to find a way to take 5 down to 0 and then go 1 further to get down to -1, right? So you're going to need 6 electrons to make this guy work. But it says that we have to do this under basic conditions. So the last time we did this, find your hydrogens right here. There's 6 hydrogens right here. Add 6 hydroxides to this side, and add 6 hydroxides to this side. The reason why we're doing that is that these hydrogens and those hydroxides, they should collectively neutralize each other and turn into 6 waters. And then this is pretty typical. There's 6 waters on this side, but there were 3 sitting on the other side there as well. So I hope I'm not going too fast, but these 3 waters over here can cancel with this 6, and there's 3 there. And now I finally have an equation for the second one. This is long and drawn out, eh? Now, this is not a 2-minute process, is it? Okay, last step. Well, second last step. We need to then put the 2 half equations together. Can I just put them together as they are? Sadly, no. This guy uses 6 electrons, this guy with 3. So double, 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 double. And hopefully you're fairly good at being organized. Like, I'm sorry if mine's a little bit messy here, but hopefully you can kind of keep track of what we got now. Put it all together. So, okay, here's 2 chromium 3 things there. Chromium 3 hydroxide solid. And we also need one of these ClO3 minuses. Okay, there's 10 hydroxides here, but there's 6 on the other side. Everybody see that? 10 hydroxides over here, but 6 on the other side. So we're going to need 4 hydroxides as a reactant. Okay, in terms of water, there's 3 water over here, but there's 8 on the other side. So we're going to need 5 waters as a product. You're going to need 2 chromates and 1 chlorine. I think that does it. That's a lot of work to balance an equation, by the way. I show this to you mostly as a backup method. I sincerely hope that you don't have to go through the rigors of trying to do this, because it's time consuming. There's a lot of other places you can mess up. But in theory, you might need to do this to try to balance an equation. You may just be able to look at it and go put a 2 there, put a 4 there, put a 3 there, put a 1 there, and you're good. But if you are absolutely just lost, first I would actually advise move on. Do this last. Because if it's going to take you 5 minutes, don't waste 5 minutes worth of time on this question. Like, do this at the end of the test, if that makes sense. But this is kind of your in case of emergency, break glass. This is that glass. Because it sucks. So, let's just do a quick spot check to make sure it fits. 2 chromiums to 2 chromiums. 1 chlorine to 1 chlorine. There's 2 hydrogens plus 4 more, so that's 6. Uh-oh. Oh, there's a 3 right here. Ooh. Okay. Okay, there's 2 times 3 hydrogens for 6 hydrogens, plus 4 more for 10, which is what we have for hydrogen. There's 10. There are 6 oxygens, plus 3 more makes 9, plus 4 more makes 13. And then there's 5 and 8, which is 13. In terms of charge, there's 1 negative here, plus 4 more there for 5. 2 times 2 is 4, plus 1 more is 5. I finally have this stupid thing balanced. That sucks, eh? Like I said, this is the in case of emergency break glass swap method. Because I hope you don't have to. Can you guys give me one more example, then we'll take our break? Sorry, I know it's been a while here, but I've only got one left, and this one isn't nearly as long. What? Oh, right, I changed my notes up. You guys do have D, right? Okay. Okay, there is one more method. It involves using oxidation numbers. Sometimes you can do a hybrid. Rather than doing all of that rigmarole of like breaking things up into 2 half equations, trying to balance them, sometimes it's easier to kind of do half inspection and half oxidation numbers. So let me show you the last method here. Let's find the oxidation numbers of this particular equation here. So this is actually a very typical question. Here's an equation that's not balanced, and they might ask you, what are the coefficients in front of all these guys? So you could try and look at it and go, okay, let's put a 2 here and a 2 here. But do you kind of get what I'm saying here? Like there's a really good shot of you getting stuck in a loop, and you're never getting out of that loop. So let's do oxidation numbers. What's the oxidation number of a hydrogen? +1. What's the oxidation of oxygen? -2. Okay, so let's work backwards. Based on that logic, what's the oxidation number of nitrogen need to be? We have +1 and -6. So, yeah, +5. I don't really care whether you call it 5 plus or +5. Some people really do. There's some people who are sticklers, but I don't care. I don't think it matters. Okay, well, you're +1 and you're -2. I don't even know what this compound is called, by the way. Some sort of arsenic acid, maybe? Never seen that before. But just to warn you, you're going to be shown compounds you've never seen before. They love to do that just to mess with you. Okay, so you've got, what do we got here? -6 with the oxygen, +3. That needs to be a +3. That makes sense. Okay. Over here, oxygen's -2, so hopefully by default, just nitrogen's +2. Well, that just makes sense. Okay, hydrogen's +1, oxygen's -2. So that's going to give you an 8 negative, but 3 positive, so that's actually a +5 for arsenic. And +1 -2 over here. So good, so far so good? Okay, let's figure out who changed. The whole point behind oxidation numbers is to help identify who oxidizes, who reduces. So hopefully you'll recognize that here's one of them. Nitrogen went from 5 to 2. So I'm going to be very specific and methodical in writing this out. If you go from 5 to 2, it means that you must have gained 3 electrons. So that's the only way to go from a +5 to a +2. You must have gained 3 electrons. Does that work? Where's the other change? Arsenic went from +3 to +5. So hopefully you'll agree that it lost electrons, but I'm going to be more specific though. How many electrons did it lose? 2 electrons. These numbers here are going to be the linchpin to getting me started. Okay. If someone gains 3 electrons, but someone loses 2 electrons, can those jive and fit together? Lowest common multiple of 2 and 3? 6. Does that make sense? Bang the wall there. So you're going to need to think about, like, well, what logically do they combine to? And hopefully you'll agree it's 6. So that means that we're going to need to multiply this reaction by 2 so that it becomes 6 electrons gained now. And I'm going to need to multiply this reaction by 3. So I'm kind of doing like a hybrid here. I'm now going to throw a 2 right here and right here. And I'm going to throw a 3 right here and right here. Everything else I have to now balance using just common sense. So let's see how it looks. So just double check though. We've got 2 nitrogens to 2 nitrogens. That works. We've got 3 arsenics to 3 arsenics. That works. So now let's try, like, I don't know, hydrogen. 2 hydrogen plus 9 gives me 11. There's 9 right there and 2 right there. That gives me 11. So at first glance, it looks like we might just need to leave this at a 1. Let's double check with the oxygen now as well. 6 oxygen plus 9 would give me 15. 2 plus 12 would give me 14. And if I make this guy a 1, because I wasn't sure what number needed to go here, but if I make that one a 1, the 14, that bumps up to 15. Now, in this particular example, it just so happened that it was a 1 right here, but we weren't sure of that. It could have been a 2 or a 3 or a 4. So basically the method is use oxidation numbers, figure out who goes up and who goes down. Use the lowest common multiple of the 2 of them to figure out how to make the electrons fit. Since I had to times this by 2 to get a grand total of 6 electrons, and this one as well by 6 electrons, it now tells me that this one and this one have to be a 2, and this one and this one have to be a 3. Everything else just balanced by looking at it. So there's my lesson. It's kind of a weird lesson. I feel kind of odd having to teach it because, like I said, you all know how to balance. You must have in order to get this far. But I'm kind of showing you some emergency methods in case you're absolutely stumped. Does that work? Okay, cool. Why don't you guys take a 5-minute break? We got about 20 minutes left. If you guys aren't aware, by the way, there is a worksheet on my website if you want some practice on this. So basically the plan going forward now, workday tomorrow, we're going to do a quiz on Thursday. Go take a break.